Forget it. We're in for a few more months of, not so warm temperature, right? So good morning. So it's not like I hate you guys that I signed this paper. I'm not sure how many of you liked it, and I don't expect that you would love the paper. But trust me, this is a very, very important concept, right? It's sort of stuck in here because it didn't kind of fit in with the previous stuff that we're doing. We look at distributed systems further along in the course, right? And we look at the companion paper, logical clocks, later. I didn't want to give both those papers on the same week because then it's going to be hard. So I'm kind of distributing the sort of the theoretical paper, right? And so it's a Hall of Fame award winner, but more importantly, the way I see it, I think I was telling him, this is sort of like when you first took data structures class when you're in undergrad, 101 or something, when somebody was teaching you about like bubble sort or quick sort or something, right? It's sort of in that kind of thing where when people taught you like, this is bubble sort, then they sort, quick sort, then they sort, like skip this and all those things. You kind of go through all those stuff. You kind of know the algorithms. And I'm not sure if you actually knew all the stuff they're talking about, but you sort of don't grasp what it's used for. And the books probably don't tell you all the conditions where you can use the bubble sort. It's sort of like kind of left it in abstract. So I can see a lot of you kind of wanting some kind of a real world example to see how these things all fit in. And how it feels so abstract that it can be used for anything, right? Not specifically for computer systems, but for anything. But I think that the point of the paper is it can be used for anything you want, right? You just have to understand what it is. And the way you use these papers are, if you ever build systems which you want to be slightly fault tolerant, and you kind of muddle through using heuristics and using what you think, then you sort of look at these papers, kind of get the ideas to see how things work, right? So that's the context of what you look. So I don't expect you to understand word to word because it's not designed like that. It's designed more of you have a vague concept of how things work, but when you're doing actual systems, you try to fix those things, right? I have a nice quote from Leslie Lamport, who's one of the really big people in this kind of a field, on how one of the projects was trying to trash them, but essentially that gives a flavor of what we're talking about, right? So the citation said this is sort of the one which started it all, in terms of replication. And it led to a whole bunch of work, and I'll tell you what those different works are. Again, the whole notion of distributed systems is way beyond this course because we have a course on distributed systems. How many of you are taking the distributed system course? There's only 3 of you taking distributed systems course. But if you take a distributed systems course, basically you would live and lie with all this stuff. You need to understand all the things we are talking about here. And the real distributed systems work is extremely boring or complicated or putting you to sleep kind of stuff. So if you don't like this this paper, if it kind of put you to sleep, whole bunch of papers in distributed systems essentially put you to sleep. But that's because they're important concepts you need to understand because the whole thing gets complicated, right? And one of the things that somebody mentioned was this is probably applicable for distributed systems, maybe not for other stuff. I don't think it's true. I think it's true for any things where you try to get some sort of fault tolerance, for the same applications or whatever, right? There are a lot of examples of where these things are relevant, right? And you can think of anything from, so one of the examples was one of the authors of the virtual synchrony paper. They sold their company to Wall Street something for $1 billion in '93. I don't know if it's just his part of the money or the whole company, but that's a big amount of money in '93, especially before the bubble and all those things, right? So these things are necessary in terms of your Wall Street, your banks, and all the critical systems, and your grade systems, and whatever system that Notre Dame runs behind the payroll and banks and all those things, right? But it's still abstract. So can you think of some examples where this sort of a thing is relevant to you, right? If we look at the notion of, so one of the things that one of you mentioned was we haven't talked about the cost of replication, right? Cost of it seems like you have to make an awful lot of replicas, right? So what is a computer program, a computer system that you can think of that processes information that is so useful to you that you're willing to pay any cost, any reasonable cost at this stage in your life? Can you think of application where you would say, without that application, without the data that it has, without the information that it stores or processes for me, my life would be pretty complicated? So that kind of rules out hello world and stuff, right? I mean, hello world programs is kind of out. And I think that also rules out the programs that you write for homework projects and stuff, right? Nobody that I know grades you on whether it's fault tolerant or whether it's reliable and all those things. As long as it sort of works, it limps around and makes one output that you can show to the instructor, you get your A and move on, right? So going beyond that, what is the application where you depend on it? Your life depends on it.
Electronic medical records in the hospital.
Okay. So yeah, that goes back to the infrastructure stuff, right? The electronic medical. Yeah. So the infrastructure, electronic medical records and banks and all those invisible servers in the back kind of stuff, right? But in terms of what runs in your machine kind of thing, because I don't want it to be, I don't want it to sound exotic, some sort of thing like, yeah, Wall Street banks should run this, but I can kind of, I don't need this for other scenarios kind of stuff, right? I suspect that most of you don't have any application like that. Most of you kind of worry about the cost of the machine more than the information which is stored. Is that a fair statement? That most of you are worried about the making one copy rather than worrying about the fault tolerance behind it, fault tolerance or reliability behind it, right? I think we are a weird demographic, right? You know enough about computers, but you probably have no money, so you don't, and you think that your time is free, right? So you would rather spend the money on the hardware rather than on the stuff, right? It's not indication on where you are, but that's typically where the students and faculty tend to do. I mean, we kind of worry about do some sort of backup and stuff, but we kind of move on, right? But when you go to real world and you're trying to do real stuff, you want to get a sense of what it is that you're doing. I mean, information is all that you really care about, and you want to make sure that the information that you store, you can say something about it, you can say something about reliability and all those things. So when you build software, you build reliability, or you build some notion of recoverability from that, right? So what are some of the simple ways that you can think of to build fault tolerance into systems? If you were to design a system for I don't know, like small business or something. Somebody asks you to say, I'm building the system, I want some kind of reliability. How would you build it? What is some technique that you can think of? You must have done it because that's some of the techniques are very common, right? What do you do to ensure fault tolerance or reliability in your own desktops or laptops? Yeah.
Running a RAID on my hard drive.
Okay, yeah, running a RAID. So essentially, you're creating some sort of a replica, right? Yeah, that's an excellent point, right? And as you're aware, there are different kinds of RAIDs, and they have different kinds of stuff, right? And what else?
Control S a lot.
Yeah, save a lot, right? Yeah, save your copy a lot, and usually your programs, when you save a file, it creates a backup version of your document, either moves the old version before it saves a new one or something. So it's trying to do some sort of reliability, right? It's trying to, if something's failed, it's trying to do something, right? So saving file, flushing the buffers, you do a lot, and creating some sort of replication that you can think of, like in the hard disk sense, you tend to do that. The other example is backups, right? Most of you should be doing backups. You create backups, and backups are really a replica, right? If you do the backup, right, you're creating a replica of the contents at that point. So the replica are not consistent, but you're trying to do some sort of a, so if you do a backup every night, so the replica is consistent as of that time, right? So you create this stuff, right? Right? So you do think about replication, you do think about the stuff. You don't think about it too much because the cost apparently is not that much to you, right? Except, of course, if you work on a thesis for 5 years and then like the one copy you had vanishes, then you will realize it. But most of us have backups and stuff, so you cannot get around, right? This goes beyond that because they want to understand what happened. So, for example, in the case of ECS Control S, they want to understand what is it that he's trying to prevent and how it will prevent, and what is the amount, how frequent does he have to do the saving. Rather than going through and giving the answer in time, they're trying to figure out what is the fundamental processes which are going on, right? And one of the problems with the abstract stuff is you tend to get lost on some of the details on. So some of the things look more complicated than they need to be, and we'll hopefully fix that, right? So again, this is part of 2 papers, and one of the reasons that you'll probably read, so no paper in distributed systems is complete without reading about logical clocks, and this paper, and then Paxos and virtual synchrony and Byzantine replication. Byzantine faults is a perennial topic in SOSP. There's at least 2 or 3 papers, and it's super hard, as you can kind of imagine. This paper only talks mostly about failed stop stuff, not Byzantine, because it gets much more complicated, right? And the reason why this is in systems and not in algorithms is because they want these systems to be practical, right? Even though they make no explicit arguments that these are practical, they show no graphs to show these are practical, but the argument is these things are practical. That's why you should care about it, and that's why this is not in the algorithms class, where, I mean, as far as I can tell, this could have been in the algorithms class too, but it's not because of your trust that this is based on is implementable stuff, right? And the reason is these people who are writing this are in systems. So basically, the argument goes, these guys are in systems. They've been building systems for a while. So since they say this is practical, let's assume it's practical. But that's the sort of things which go, right? There's really no proof. So I hear you, many of you say there's no proof, there's no proof to show this stuff. But essentially, their argument is we've been building systems a lot longer than some of you were on this face of the earth. So we kind of know how systems work. So we kind of know this is what is really happening. So we kind of think that the solution is practical. So trust us, right? And most of us trust them because Leslie Lamport is sort of, and among others, right? So let's look at, so I see one of these papers as hopefully if you're going to build any kind of systems in the future, any kind of, not just operating system, but any kind of programs and stuff, you will have this in your bag of tricks, and you'll probably look at it and kind of say, oh, maybe I should have used some of these ideas. So let me look at the first one, right? So it's a basis for Paxos. Unfortunately, you should really take the distributed systems class to go through all the different systems. But one of the things that people are very excited about is the notion of a Paxos, right? So Paxos algorithm, the reason I have this quote is I think it gives a sense of what really happens when you build systems, right? So here, somebody was building Echo at CERC, which is Digital Equipment Corporation's System Research Center, which in its heyday was considered sort of the best place to work for systems research. There's Xerox PARC and DECCERC. So this is sort of the best place to work on for systems. There's a few people who are working on it. So they're building on a file system called Echo, right? These are very smart people, let's assume, and they're building this fault-tolerant file system, right? Incidentally, most of the file systems that we use right now are not really fault-tolerant, right? You kind of expect them to work, but things can go wrong and you're kind of on your own. And RAID and all helps you a little bit, but not end-to-end, right? So they built this stuff, and they claim that any number of non-Byzantine faults happen. They believe that this will be this will work, right? They believe that they built a system that even if some of these things fail, their system will keep working, right? And mostly because of brute force, because they know how these things should be done. So they kind of sort of fix it on the fly. So for example, the simple case, normal case is trivial, right? Normal case is when you expect no failures, things work. But when the case of failures, they have complicated ad hoc mechanism, right? And that should ring true to most of you. So when you write programs, you typically tend to write programs which are fairly simple. Then you realize that this particular stuff doesn't really work. And in the case of the writing to a file, you may realize that if you're saving to a file and then the machine crashes at the time, that only copy you had would have been overwritten halfway by your save, right? So saving a backup all the time is actually counterproductive if your system crashes at the exact time when you are saving, right? Then you realize that what you do is you kind of move the file to another file. You create a file called file.back or something. Then you save this file, right? Then you find that under certain circumstances, that's not a good idea, because when the rename, some corner case says that your rename, there's a little race condition here, rename did not go through, your file save did not go through. So all you get is a file with 0 bytes, right? It seems like it shouldn't happen, but it happens, right? I've seen it happen in the past. So when that happens, you try to fix it by creating file.back. So you tend to go through these contortions to solve the problem by brute forcing, where you find some fault and you try to address it. So they basically said that's what they were trying to do. So the goal was to build a fault-tolerant file system. It sort of works, but in the corner cases, let's assume they are very smart people. So they think through all the cases and say, okay, for this case, if it happens, I'm going to fix it like this. And this case, if it happens, it's going to happen like this. So Leslie Lamport, who is more theoretical in nature, he wanted to prove that their claim is wrong, right? He wanted to prove that their claim is wrong because what they're trying to achieve cannot be achieved the way that they're doing, right? That's his goal, which seems like sort of like an arrogant way of going about it, right? So basically you're saying, I see a whole bunch of smart people here, so my goal is to prove all of you wrong, right? Because theoretically it's not possible, right? Actually, I don't know what happens. I don't know if he proved that they were wrong, but let's just move on, right? So this is the quote he has from his webpage. Instead, he came up with the Paxos algorithm, right? So it's the first three-phase commit algorithm, and which clearly stated correctness and proof of correctness, right? Correctness condition and proof of correctness, right? So what should have happened is you would think that the people who built Echo, right, at some point realized that what they're really trying to do is, what they really needed was a three-phase commit, and these conditions that they're laying out, you have to set it up so that you achieve your goal, right? So I suspect that if you read the Paxos paper without having that experience, you may not appreciate it as much as if you come to it afterwards, right? It's possible. So if you look at it as the three-phase commit protocol, it looks sort of boring because they basically say you got to do this, you got to do this, you got to do this, you got to do this. But if you look at it from the context of how it applies to your Echo file system, whichever you're building, then you realize that what you're trying to do here is essentially a three-phase protocol, and you kind of go with the stuff, right? So that's the nature of the stuff. Essentially, what they were. So this is the Paxos algorithm, right? They have a bunch of processes which have to come up with a value. They have to choose a value, right? They have to come up with a value that all of them kind of agree on, and they set up some conditions on what is the deal, right? So the consensus is all of the replicas have to come up with one number that they all agree with, right? So it looks like it's in the abstract sense, but it may happen in practice. So if you're running if you're running an operating system on multiple processors, where the kernel is running on different processors, right? They may decide what's the next process ID to allocate to a new process using the Paxos algorithm. They may try to decide what the number is, right? So one way to achieve that is for somebody to decide that your process ID should be 10, and I give it to everybody else. They're trying to look for a distributed approach, but everybody proposes it, and then you go through negotiation to figure out what the value is. They set up some condition, right? The conditions are all of them are individually able to choose their values, right? Only one of those values that were proposed will be chosen. So you cannot choose a value which is not proposed by anybody else. And only one value is chosen. So you have to choose one value that is proposed by somebody. It's not saying whose value should be picked. And all the other processes do not, when they know that something was chosen, that's the final one. They're not allowed to retract from it, right? So in the notion of if I want to implement this for a kernel running on multiple processors, and I'm trying to come up with a unique process ID, right? What that means is all the processors choose some ID, right? And you're allowed to pick only one of them. You're allowed to pick them in a fairly optimal fashion. That's what the algorithm would say, right? And the other processes would not know unless it's a final number. So you're not allowed to say the process ID for the new process is going to be 10, but then you say, oh, no, actually it's 100 because I finally heard from this other processor who just woke up, kind of stuff, right? So it's elegant way of looking at the stuff, but you apply it in the case that you are trying to do like that. So if you ever have a problem of finding out what the correct number is, then you will run this algorithm, right? How many of you return distributed programs? Distributed also means multiple programs talking to each other. So it could be multiple programs on the same machine talking to each other, right? How many of you? Or 2? I suspect you would be, right? Because if you said you're working on Condor and stuff, right? So Condor basically breeds, it's a distributed system, right? So you need to understand what the semantics are. So essentially that's the stuff, right? If you read the Paxos paper, I was thinking of assigning it. I think it's still in the further reading list. The algorithm itself is horrendous because it kind of goes through the step of what has to happen. But the problem that you're trying to solve is fairly simple. So the virtual synchrony, this is the one that was sold for a lot of money, right? So this is essentially, there's a lot of words, but essentially it's trying to do reliable multicast, right? Multicast is essentially, it's a networking phenomenon. So where we decide, you have a group of users, right? So let's say we decide all the people in these two columns are part of a group. So I want to send a message to you guys, right? So I want to send something. I want to say, okay, hello or something. I want this stuff to be received by all of you reliably, right? And I want it to be received in the order I sent. So if I say 1, 2, 3, I want it to be received in the order of 1, 2, 3 to each one of you. And think of it in a more general fashion. All of us can talk to all of us. All the messages that all of us send will be sent to all the other nodes in the order that it was sent. And in the order that it's received in all the other nodes, right? So the problem quickly becomes pretty complicated because there is really no notion of absolute time, right? And we'll see the logical clocks and stuff later on in a follow-up paper. But essentially the idea here is it does not matter who came first. All that matters is whatever order we created is the order in which everybody else should get it, right? So you form a different group and they maybe have different overlaps and groups. So this is the notion of multicast that you read from networking classes, right? The pure multicast that people talk about networking has no notion of order or anything. They basically say, we'll send it, all of you will get it in some order. One of you may not get it, what have you. But here it's a lot more stringent where any message is sent will be received by all of you at the same order, right? Why would a Wall Street company spend a lot of money to get that technology? Can you think of application where that's useful? Yeah.
Executing trades.
I'm sorry?
Executing trades or offers for current pricing stocks.
Current pricing of stocks, right? Yeah, I'm not sure about the executing trades, right? So executing trades would mean that so it depends. So the order has to be on all the replicas, and that's one part. Sending out the codes, right? So if I'm a stock exchange, right, and 3 people are buying stocks, right? It does not matter who won, right? Let's say the price keeps changing, right? So for the single stock, person 1 bought, person 2 bought, person 3 bought, person 4 bought, right? It's not important which one bought in which order, but all of the buying has consequence, right? So if the first one bought all the stocks which are out there, second one cannot possibly purchase because the stock is sold out, right? Or something like that, right? So the order is important, right? So if you're all the stockbrokers on the floor or something and you're running computers, right? So if I say something, if I say stock was bought or something, all of you should get it in a timely fashion, which is why they spend a lot of money for it. But the problem is all of you should get in the same order that it's being sent, right? If it's in a different order, then it'll look like first, my order goes to him first, and somebody else's order goes to him first. So, he may purchase his order, my order, this stuff, right? So that's all the way be it. But essentially, it's reliable multicast, where you can guarantee the order in which the messages are received by all the group members, right? And that's a pretty powerful thing. It was published in SOSP 87. Again, unfortunately, this is not. We're not going too much into distributed systems. We are still trying to stay within this operating systems, but kind of know what the other problems are, right? I didn't assign it to the class. I don't expect you to follow through. But if you ever want to build any kind of systems, you would look these things up, right? Because if you don't, then you'll end up with what Leslie was talking about. You'll muddle through with all the stuff, and essentially you want some reason to believe how things work, right? The Byzantine generals problem. How many of you heard it from your undergrad class? In which class? Sorry?
So they wouldn't discuss it in classes otherwise.
Okay. Always I try not to discuss it because it gets pretty bizarrely complicated, right? So have you heard of Byzantine fault, Byzantine generals problem before?
Yeah, yesterday.
Distributed systems, yes? Huh?
Somebody, explained the problem to one person in my group, he heard about this before and
Okay.
explained it to us.
Okay. Okay, so distributed systems live on Byzantine systems, right? Byzantine is the problem. If you read Leslie's stuff, right, he wanted to come up with something like a dining philosopher problem, right? Everybody knows dining philosopher problem. It's a good problem that everybody sort of knows, right? It represents some complications going on. It represents the deadlock phenomenon and stuff. But you explain it using this metaphor which captured people's imagination, right? Where the philosophers can eat spaghetti or rice or, it could be fork or chopstick or something, but you still capture what's going on, right? So you wanted to come up with something, and that's why the Byzantine general problem, right? The Byzantine general problem, I think it started off with the Armenian general problem. There's some historical things to it, but then they had to make it politically relevant and correct and all those things. The idea here is you have a bunch of generals, right, who are trying to make a decision, right? You have a bunch of generals who don't go into the same room, but they are trying to decide something to happen. So they're trying to send messages to. Let's say they're in war, and they're trying to decide what's the best course of action, right? So you have, let's say, we're all the generals who are in this room, and we are trying to decide whether we should attack or whether we should leave the class right now or we should wait till the end of the class, right? So the assumption here is some of us are loyal, meaning we will do what is the right thing, right? So whatever the right thing is, let's assume the right thing here is we should wait till the end of the class. So some of us will decide the right thing. We'll do faithfully what is required of us. Some of us are traitors, right? Some of us are the Byzantine generals who want to sabotage it, who want to do something that is not what is right for the group, right? But they don't want to reveal who they are, right? So they don't want to stick out. They don't want to always go against the whole the consensus, because if they did, we'll know that they are the traitors. So we'll, let's say, chop off the head. So they don't want that. So they want to act. So they want to act such that I can't predict what they're going to do, right? So let's say half the time they decide the wrong thing, half the time they decide the right thing, right? So statistically, I have no way of knowing whether they're lying or not. So those are the generals, right? So their goal is to make sure that we do something that we're not supposed to do, right? But they're not coordinating with each other. So they're not like colluding with each other to say, for when this vote comes up, let's all join together and go against it by saying we should leave right now. They're acting independently. They're trying to act where they don't reveal what their motivation is. So I can't know, looking at the votes, know who's good, who's bad, right? And that's what I'm trying to do, right? And that's the Byzantine general's problem, right? The problem is there are some who are malicious or some who are untrustworthy, who are doing something which they're not supposed to do, and I'm trying to figure out. So I assume that there are certain nodes which always do the right thing, and I assume that certain generals who are doing this bizarre behavior, trying to knock out the system, and I'm trying to build consensus. And the way you build consensus is you find the majority, right? I do whatever the majority will do, right? So I need to. So we'll see how we build that. But essentially, this is the problem, right? So when I say it in that abstract fashion, it looks like there's some blood and war and stuff going on, right? But I think in realistic sense, that's actually much more relevant, much more what really happens than anything else, right? So you're basically saying when you build these components, you don't really know with certain guarantee what things are supposed to do. And we'll see the other approach, which is the fail-safe model, right? Fail-safe model is easy to understand, easy to explain, easy to analyze, but I think it's completely theoretical, right? The fail-safe model is one of the other things which is described in the book. So what's the fail-safe model? Failure model. What's the fail-safe failure model?
Fail stop.
Fail stop. Yeah.
So it's when if some node has a problem, then it stops running. You never see the output.
Yeah. So fail stop. The node which is creating a fault knows that it creates a fault, and then as soon as it creates a fault, it'll stop, right? So what that means is all the decisions I make till the failure is correct. All the decisions I make after the failure would be wrong, but I should shut myself down. So I need to be able to recognize that I made a fault. So I need to have internal stuff to know that I failed. So the owner, so the person who's supposed to know that is me. So I'm supposed to know that I failed. If I fail, I take myself offline, right? So every decision I make till the point I fail is correct. At the point when I make a failure, I shut myself completely so that I don't influence anybody else, right? So when you assume that model, you're expecting these systems to know what failure is, to completely fail all at once. You don't fail halfway through. You don't go through a undefined phase. You completely fail, and then when you fail, you shut yourself off, right? So everything you did before that has to be valid, right? And when you think of it in real systems, that's very, very hard. Usually when you write programs, you don't know when things are going wrong till you made some mistakes and you've kind of violated the principle, right? The thing about Byzantine general problem is it's sort of smells like random, right? You don't expect any particular node to be behaving a certain way. You just believe that in the whole sense, in the whole system, certain number of nodes, certain number of decisions would be wrong. It doesn't matter who those things are. So every time we make a decision, like my first question, all three of them can be the Byzantine generals. The second question, all four of them may be the Byzantine generals. So we don't really expect which node to, the node's role is not fixed. They may fail and not fail in different ways. One node can completely fail. So the notion of the fail stop one is subsumed by the Byzantine fault because if one node keeps failing, right? So this is much more general, much more realistic, and much harder to analyze and deal with, right? So did that make sense with the Byzantine general's problem? So it is described in a fashion similar to your dining philosopher problem, right? So don't get caught on whether the dining philosophers eat spaghetti or they use fork or chopstick or something, right? The key here is you're trying to understand what is really going on. And what is really going on is you expect these failure systems can fail independently in random fashion. As long as a certain number of nodes are doing the right thing, you will be able to proceed. And the way you proceed is very simple. The way you proceed is you do a vote, right? The majority always wins, right? So basically, general problem, the solution is very simple. The solution is you find the majority, right? The key is understanding how many numbers of nodes you need to achieve a certain amount of reliability that you want, right? So those are the three systems that sort of came out of this stuff. I mean, the ideas were there, but this one is actually a tutorial, right? So they kind of encapsulate these kind of systems, right? So anytime you build anything which involves more than a single piece of stuff, you should be worrying about this stuff, right? And you will worry about it if you build systems for whatever. If you worry about it if you build systems for healthcare or your database, all those things. But even for anything else, right? If you build systems that somebody really cares to buy, you need to have a sense of what is the failure and how you deal with that. And as we kind of saw, all the systems do have a notion of failure. I mean, even the simple case of copying a file over and over again. And the ideas that are described in this paper should help you build better systems, right? So you're not going to exactly implement. So there's no source code library which goes with this paper. You can't just put it into the stuff. You need to kind of map whatever problem you're trying to do into what they're talking about, right? So you may have to say, in my system, I'm going to do X, Y, and Z. And X looks like the sort of things I'm expecting behaves more like Byzantine general's problem, because the nodes can fail, not maliciously as in the examples we talked about, but because the way that they're capturing stuff, the failure model would more be like Byzantine, because it's sort of like a random, right? So when you realize that, then you realize, okay, if it's Byzantine and I expect 3 of the nodes to lie, right? Because I say I'm putting a sensor node, right? I have 3 sensors out there and they're giving me answers, right? I can build all kind of security to make sure that, I don't know how many of you know about sensor networking. So sensor networking, the idea here is you put lots of sensors and you do something with it, right? So I want to find out what's the temperature in this room, right? So let's say I put a lot of temperature sensors in this room. I'm trying to find the average temperature. I want to find out all the temperatures and add them, right? If you think about it, you would imagine you put sensors in every table, and then you find the average. You find the running average of all those stuff, and then you get the answer, right? So in that case, there may be a bug, there may be something happening that one of the sensors is not giving the right temperature, right? So it may happen that this is saying this is 70, 70, 70, 70, 70, and that one says like 1000, 60, something like that, right? And it seems obvious that 1001 is lying, so you can throw it out, right? But it could be more insidious. So it's going to be 70, 70, 70, but actually in this part of the room it's 90 or something. So it's not very, let's assume it's very hard to understand whether some node is lying, right? Not intentionally, but because it's malfunctioning, right? And you want to find the average in this room, right? If you look at the simple papers on this one, they'll do this averaging. They'll average all the numbers, and then they'll say, oh yeah, if somebody says the temperature is 1000, it's outliers, you should drop them, right? Right? I don't know how many of you have seen those systems, but essentially that's what they try to do. Say, oh, let's drop those. Let's drop the max and the min and all those things, right? But essentially, what you really want to be doing is thinking about this as a basically general problem, because it's not like these nodes are maliciously doing something, but they are for whatever reason they're not giving the accurate temperature. And to get get a good answer, you have to think of it as a basically general problem. And you need to find out, use that, right? The first generation systems don't do that, and they're kind of okay. But so when you think of sensor network, hopefully you look at this and go like, oh yeah, that's a basically general problem. I know that means that I need 2t plus 1 replicas. So if somebody says I need to put 1000 sensors in this room, you will say, well, it's really 2t plus 1. I expect blah to fail. So even though you have 1000 sensors, I can only get the answers from 100 of those because of something, right? So that's where you would want to take this, right? Does that make sense? Right? Can you think of, in your own field, in your own thinking, can you think of another application where this happens? So let's say in grid computing, right? So I'm picking on you because you're a grid person, right? So grid computing, one of the things you do is you run your program on a whole bunch of nodes, right? So you run your program in a whole bunch of nodes, and you sort of get the answers and you kind of put them together, right? Who else would be using that? Who else would be using grid computing in this class? Grid computing concepts for doing their research. Who's working on like data mining or image processing and stuff like that? So he's using one. What do you use with it?
It's mainly related to computer vision.
Okay. So computer vision, right? So he's doing some processing on all these machines. So his goal here is to, he uses 1000 processors in Notre Dame to do something. So he sends it all to different machines, and he gets getting the answers, right? So can he trust the answers from from each of the nodes that are coming in? Can you trust the answers that come from each node?
Yes.
I'm asking him because because it's his application, right? So I'm guessing.
Yeah.
You can trust?
I guess he should be able to trust.
Okay, but for the rest of the class, should he be able to trust the algorithm in each of the systems? If you take a problem and send it to a whole bunch of machines, should you be able to trust the answers which come from each of the machines? Yeah, so each of the machines are not owned by you, right? So they're owned by somebody else. They're running different operating systems and all those things. I'm allergic to dust, and I shouldn't have been holding it, right? So should you be able to trust the answers?
I mean, in good faith, we can just, the result we get back from the nodes. But if you do something like over the internet, like, floating at home, things like that, I think you need to, run the same set of data, multiple times, to make sure that you get it.
That's an excellent example, right? So the folding at home and all those things. How many of you use those things? Folding at home, SETI at home, and all those things, right? You basically run these, like there's some foundation which sends this stuff to you, and you run them, and then you send the results back, right? And he said, you cannot trust these answers because it's going on somebody else's computer, so you're getting some answers. You don't have, you run multiple times, right? Essentially, what they're trying to say is how many times do you have to run to get that, to trust it, right? That's essentially, that's the crux of what they're trying to do, right? So if you run that, so because clearly the polling at home has to be able to run it more than one time, right? So if you send it to one machine, get the answers, it might have been that you're all Byzantine generals, so you might have lied either by saying that yes, there's an alien, or no, there's no alien. So if I want to get some sort of a confirmation, I have to have a model and then say, this is how many times I have to run, right? You don't want to run it too many times, right? I don't want to run it like 1,000,000 times each data just to be sure of what the data is, because that will probably good, but then I won't make any progress, right? So how would I decide how many times should I run in the case of folding at home?
I have no idea.
But how, actually it's in this paper, how would you go about deciding how many nodes you should run?
It depends on team, right?
Yes, T, right? And so how do you do T? I think one of you mentioned in the reviews, right? How do you know T, right? That's not written in this paper. You somehow magically know, right? You have to know how many nodes in general are trustworthy, right? Right? And this paper says nothing about how you know that, right? So if SETI at home assumes that 10% of the nodes are not trustworthy, are Byzantine generals, then they have to plug that T into the 10%. So they say, okay, we have data for 1,000,000 nodes, and then 10% of them are whatever, so that they know what the T is. They can calculate what the number should be, right? So the hard part is coming up with that number, right? So I don't believe that even within our campus, the answer is T equals 0, right? T equals 0. Okay, the number of untrustworthy nodes is 0, right? It's probably smaller than the case for folding at home, right? So I expect that if I send them my data to within Notre Dame to a CRC and like to 1,000 machines, I expect that I can trust those answers better than if it's a folding at home and I'm sitting across the continent, across the world, right? But that doesn't tell you exactly what those numbers are, and that's the hard part. So you as a developer would have to come up with what the number is, and all this paper tells you is if you know what the number is, then this is what you have to do, right? Hopefully that's a little bit more concrete than what they're trying to say, right? So that's the Byzantine general problem, right? And intuitively it seems like when you say, I'm going to send my results to a whole bunch of nodes across the planet, I'm going to get the results, right? Intuitively, we all can say, I can't possibly trust all the answers, but how many should I know is the right thing. So that's why you have to come up with, right? So the fail stop is that you know exactly when things, no, the node which fails knows that it has failed. It never gives you half an answer, which is half correct. It either gives you a correct answer or it stops. So if it ever talks to you, that message is always correct, right? So even though it's easy to understand, it's theoretically kind of, practically it's on shaky ground, right? Because you rarely know whether something is wrong or right. What happens more is the Byzantine kind of problem where it's some probabilistically something happens, right? So, and they say you need T+1 copies of replicas to make this system reliable, right? So what is the intuition behind this T+1? Where T is the number of nodes which fail, or T is the number of nodes which are lying, right? So which kind of, somehow you kind of know this. So why T+1? Yeah?
You only need one node to function. Yeah, functioning system.
Yeah, so in this system, you're not voting, right? So you assume that if a node talks, it's valid, right? If a node says something, it's always valid. So if a node was to fail, it'll fail completely without saying any answer, right? So in this model, if T components are supposed to fail, in the worst case, if all the T nodes fail, you need at least one more to come back and answer, right? So in this assumption, only T can simultaneously fail. So if you assume that T is 100, if you assume that if I send it to the CRC cluster, and in the worst case, 100 of them can fail, I need at least 101 because I need that extra one to answer the stuff, right? I don't really care about where the answer comes from. So even though all of them gives me the answer, I'm just going to use any of them, right? Because since of the fail-stop model, any answer is good enough. It's just that I have to do it that many times, right? Does that make sense? So when folks had questions about replication cost, right? Is there any way, if you assume this, is there any way you can get away from this, right? Meaning, when I'm sending it to the CRC cluster, I expect 100 nodes to give me bad answers, right? Can I get away with using less than 101 different replicas of the same computation? Even though 101 is a large number, can I get away with making it to 99 or 98 or something? Intuitively, I mean, theoretically, you can probably prove it, but intuitively. Yeah?
Well, you just get rid of the computers or the nodes that are functioning improperly, and then you've gotten it down.
Yeah, no, but that's failing, right? So the point is, it's incredibly wasteful, right? Because in the normal case, you are creating 101 copies, because in the worst case, you expect T of them to fail, right? Fail-stop model does not say that the T will already fail or T will fail all the time, right? Fail-stop only says that the probability that you'll get bad answers in the worst case is T nodes, right? So it's highly impossible that all the T nodes will fail all at once, that you're left with one person, right? It's likely that one of them fail, two of them fail, or three of them fail, or some percentage of them fail, but not the whole thing, right? So it's incredibly wasteful because now you are repeating the same thing so many times, even though the probability that all of them fail may be small, right? The probability that all of them fail simultaneously may be 1 in a million, right? But the model says that if you want to be sure, you have to run it 101 times, right?
Well, then shouldn't you only need one computer at a time?
Well, you can do it serially, right?
Right. So if you have a timeout value, and then you run it, and if no answer comes out within the timeout value, then you just run it again on someone else.
Yeah, so you're paying the cost somehow, right? So if you do it parallelly, then I have the same amount of cost, but I need 101 machines. If I do it serially, so in this model, I run it once and see if the answer comes back. If not, I run it again, run it again, run it again. So it guarantees you that if you have the right T in the serial model, at the 101th time, you will always have the right answer, right? Except you may not have to do that, but it guarantees you that, right? So that is important, right? What is the practical implication of this? You have built some, in your life you built some things, right? If I tell you that for his case, for the pattern recognition stuff, I tell you that the T for our cluster is like 5, right? That means the probability is like 5 machines can die at the same, give you the wrong answer or something at the same time, right? Which means that for each computation that he does, he'll have to do it on 6 nodes, right? Which means that whatever he wanted to do, whatever recognition he wanted to do, now you're doing 6 times as much as what he has to do, right? Would you do it 6 times over? No. Why not?
It's a linear factor.
What?
It's a linear factor.
It's
not a big deal.
So you live on the edge, right? You live on the edge based on what the value of this data is, right? I think you're living on the edge, right? I think you need to understand that in that particular sense, you have to really run it 6 times. You may realize that practically this is impossible. The computation, there's a fixed cost. So if you go and tell your advisor that, I need to run it 6 times longer, right? Which may mean that somebody has to pay 6 times the computer cost, or it may take you 6 times as much time to graduate, right? How many of you here would like to graduate in 30 years, right? I'm guessing not too many people, right? So if you put it in that terms, right? clearly something has got to give, right? So it either costs you 6 times longer, or if you do follow the sequential model, it takes you 30 years to graduate. So I'm sure some of you may not want that 30-year thing. So you make decisions and say, I'm just going to run it once, I'm going to live with that, right? But the reason why we're reading this paper is for you to at least understand that you're taking a risk, what kind of risk you're taking, and then moving on, rather than assuming things will work out, right? Yeah?
I guess I'm just kind of curious. Like, how is this the first time they proposed like the notion of Byzantine failures? Because it seems that like aviation and those industries use redundant systems for control services for a lot longer.
So this is one of the things that we were like having off the camera chat, which is essentially it looks like it doesn't have to apply to computer systems, right? So as said here, it doesn't seem like it applies to computer systems. It can apply to grid computing. It can apply to flight controllers, and they've been doing flight controls for a long time. And it should apply to bullock carts and all the way back through, right? Do you guys think that this applies to everything that you can think of? Not just computers, right? Back in some Byzantine time, somebody realized that the probability of failure of 3 wheels is something, or they added extra wheels and all those things, right? So is this a new concept, or this concept was always with us, and this quantifies, it tries to understand what those stuff are, right? I think that's essentially what happens, right? I'm sure I'm sure that he thought. I mean, I don't know. Like when you mentioned that SETI at home has to repeat it a certain number of times, right? I didn't know if you thought about it because you thought about it as a Byzantine general problem, or because it seemed like the obvious thing to do, right? You kind of do it over and over again because it seems like that's the right thing to do, right? So I suspect for a long time we just did extra stuff because it sounded like some things will fail. So the way we need to, so we recognized a lot earlier that 1 is not good enough, right? If you want some sort of fault tolerance, you have to do it a little bit more. But all this is trying to say, if you really wanted fault tolerance, this is the upper bound of how much you need to have, right? So I don't think this is restricted to computer science at all, and all the airline stuff. So if you talk to them, they'll address the same issue from their perspective. And they'll say the same thing that what we said, right? If you prove that you need 6 times as much, if you prove that the wings, you need to have 6 wings just to be safe 100% of the time, right? You have to then look at the cost. And you have to figure out, whether you want an airplane with that much of reliability and stuff, right? So I'm sure the airplanes are not designed to be 100% fail-safe, right? But you do some kind of a stuff to figure out what the probabilities are, and this is what you're trying to do. And I think this is valid. I think they give some examples along those lines along the way to right control systems kind of thing, right? But yeah, it's the same problem, right? But the goal here is to understand what the upper bound is, and go with that. And necessarily they have to be vague on what T is and how you measure T, what it means to you, right? I think in the case of fail-safe, it's even harder because I can't think of a single case where fail-stop works, right? Where the system knows it's failed and it completely stops itself. I think they give an example that the hydraulic wing knows that it failed and it kind of drains all the fluid, so it stops, right? But then that thing may get stuck and then things get kind of bizarre, right? So Byzantine general system, if you expect T components to fail, you actually need 2T plus 1 copies. So what's the intuition behind 2T plus 1? You're expecting T components to fail. Why does it become 2T plus 1? Remember, for the Byzantine general problem, the solution is you vote. Right? The majority wins, right? So why is it 2T plus 1? Yeah.
If T failed, then you still have T plus 1 that are saying the right answer, so you still have a majority.
Yeah, so you want the extra 1, right? So if T fails, you want the another T to counteract this T failing, and then you get 1 more, right? But think about it. Think about what it means. Suppose the correct answer is true, right? And suppose T is 100, right? So you need 201 components to do this stuff, right? Where the answer you get might be you have 201 truths, right? So you have 100 nodes which could potentially fail. So you have 100 nodes which will not fail, right? You don't know which one is what, right? And that's why you get the 201, right? So you kind of contract that. So you always have one who will give the right thing, right? So what this means is, if the correct answer happens to be true, right, the possible outcomes of the system. What is the possible outcomes of the system?
50%.
Yeah, but numbers, right?
101 less than or equal to true, less than or equal to
101 truths and 100 false, right? All the way to what's the other extreme?
200 true.
201, right?
Yeah.
Yeah. So your system output can be 201 true, all the way to 101 true and 100 false, right? So it's incredibly wasteful because you're having that many amount of replication, but that's what you have to expect, right? So in this system, it's not possible for you to guarantee anything unless you have that much extra, right? If it bothers you, that's fine. You can reduce the amount of replication you have, but the point of the paper is you cannot guarantee anything. If you're building NFS file system, if you're building a file system for your machine where you hope it's fault tolerant, you are free to use whatever number you want, right? But if you want some sort of a guarantee that the system will always be accurate, you have to somehow measure T. Somehow we don't know how. But once you measure T, you have to have this much replication. And if the cost of replication is too high for you, you can reduce replication, but you have to realize that you're now losing the fault tolerance, right? So if you want to build a fault tolerant file system, you need to have this much of replication, right? That's a higher order bit. I mean, that's the important stuff, right? And that's one of the things that he was mentioning. Like, the people who build the Echo file system, if you don't do this analysis, you sort of think this is reasonable. I mean, whatever number you come up with, I don't think anybody would actually, create that many extra stuff. Most of you, like pointed out, I mean, you're not going to run 6 times extra copies and stuff, but you have to understand that this is what's going on, right? But there's no way you can reduce that stuff, reduce the number, right? But when you go through the paper, they add more complications because they say, well, what is really happening is you have to now trust the clients, you have to now trust the servers, now you have to trust the output, now you have to trust this, and nodes have to be added. And if you want to trust the clients, well, that's simple. Run that's a Byzantine general problem. So you have 2t plus 1. You have to trust this. You do 2t plus 1. This is 2t plus 1. This is 2t plus 1, right? So at the end, you look at that and you go like, wow, this system now needs like humongous amount of replication because everything is now replicated, right? The whole thing becomes much more complicated. The whole thing is a nightmare, right? How many of you got the feeling when you read the paper? They don't put it all together, but they basically say, oh yeah, I mean output, that's 2t plus 1, and you have to promise that they'll not be run in a certain order. Oh yeah, that you need to do this stuff, and that's another 2t plus 1, right? If you put it all together, the system becomes more complicated, right? What does it tell you about what you know about distributed systems? I'm aware only some of you are taking a distributed systems class, right? But it also applies to anything that you do with more than one component, right? What does it tell you about systems that you use using threads, let's say, or multiple processors or stuff like that, right? Does it make it seem hard or make it seem easy than what you thought before? Yeah?
I guess hard, but it seems that people just kind of intuitively pick a number based on experience versus using the actual theoretical components they should.
Yeah, it feels like people just pick some number and then go with it, right? So do you trust people's intuition on those? Again, obviously it depends on what you're trying to do, but the answer is always it depends on what you're trying to do, right? So if you're building a hello world program, I'm sure you're not going to do all this stuff, right? Even if you know it fails, you're just going to let it go, right? But for more complicated systems, right? our life depends more and more on computers, right? More and more on systems kind of thing, right? How much do you trust your systems are going through this kind of analysis, this kind of stuff? I don't know the exact answer. I'm just, I have a gut feeling of where things go, but let's hear your stuff, right? Like, for example, medical records, right? Medical records, if if an error gets into a medical record, right, it could be really awful, right? For some reason, my medical record, sometimes they change it to I'm a woman, right? Because they think my last name is a woman, they change it to a woman, right? And usually it's not a big deal because the nurse looks at it and goes, oh, okay, we have to fix it, right? But it could be something really bad that may hurt you, right? So for example, if they think that you have some disease that you don't, and your insurance may be denied because you have something, right? So you want more reliability on those systems, right? Knowing this, do you believe that these people are actually doing all the stuff, or is it still being done as, I've been in the field for 20 years or so, I don't think this will happen, right? Yeah.
Well, even if you know all this stuff, unless somebody comes up for a way to precisely compute t, it really doesn't matter.
Mm-hmm.
Because you're still going to be making a guess on t, so you're basically doing the same thing.
Is that true? So if you don't know t exactly, right, would that make this stuff irrelevant? What if you underestimate t?
If your default behavior is for the hospital case to replicate everything k times, if you know that there's, the Byzantine problem says need 2t plus 1, then who's to say that k really isn't the right number? Maybe k actually happens to be 2t plus 1. And from experience, they know that it's 2t plus 1. But they can't prove that t is k over k minus 1 over 2.
Yeah, so one of the things you remember is, like, even though we say prove and all those things, right? Real world people don't care about proof. So they just want to have some sort of a gut check whether this is true, right? So that's the excellent part, right? So let's say the Byzantine, this depends on the notion of a t, right? Which we don't know and nobody knows what it is, right? Let's assume t happens to be 100, right? Like the case we meant. So that means you need 101 extra replicas, right? And you, through sheer experience, right, know that you know that things will fail. So unless you are like a very novice programmer, you're not going to do with one copy, right? You're going to have multiple copies, right? So you might have come up with one, let's say to infinity, let's say like 1,000, right? Some large number, right? So you may add those, right? Does that invalidate the notion of understanding that you need 101? Are they in conflict with each other? The notion that you pull some number out of the bag, and let's say you chose 40, right? You could have chosen anywhere from 1 to, actually you could have chosen anywhere from 0 to 100, 0 to infinity. But let's say you choose 40, right, for some reason, right? Does that invalidate what you're trying to say?
They're kind of orthogonal issues almost. One is, yes, this is what you should do, and the other one is, well, we can't actually do that because we don't know what t is. So based on trial and error, and the fact that I've done this for k or for y years, I know that k is the correct number to choose, or I think that k is the correct number.
Yeah.
Actually, it doesn't seem that simple because if you had 100 replicas in the same room when there was a fire, then all the replicas would die. But if you had 40 replicas in different parts of the country,
don't even get started on those, right? You're making the problem much more harder, right? The notion of figuring out what's the failure rate of a component, it's very, very hard, right? So one of the things he was pointing out was if you keep all the components in the same, I mean, it's the 9/11 case, right? I could have created n replicas in the all the floors of the World Trade Center, right? Because I might have considered one thing. So that's another problem, right? How do I make sure that they are independently? I mean, all these things assume that the failures are independent of each other, right? And that's not trivial, right? And a lot of companies actually have the data across in multiple parts of the globe, trying to understand, trying to counteract that fact, right? But I mean, there's a lot more complicated stuff that we have no idea what that is, right? So who says that by you replicating one